Welcome to the deep dive. Today, we are taking on what might just be the greatest reverse engineering project humanity has ever conceived, the mind itself. We're diving into mind design, this intense endeavor to understand thinking, not just by observing it, but by figuring out its actual construction, its mechanism.
That's exactly right. It's cognitive psychology, but approached almost from the manufacturing floor.
Right.
You don't just study intelligence, you try to build it.
Right, to build an AI.
To build an AI, yes, as a way to figure out how the natural version, how we actually work.
And it's wild to think that as a serious scientific pursuit, this is barely 2 generations old.
It's so young. And the sources we're looking at show that the conceptual foundations have been, well, fluid, to say the least. It's this constant battle between pure philosophy and hard engineering.
A field of constant debate.
Absolutely. So our mission in this deep dive is to really articulate the fundamental ideas that made AI possible in the first place, and then to map out the active fault lines, the conceptual disputes happening right now.
And we have to start with the biggest question of all.
How can matter think?
How can mere stuff have a mind? That's the classic hurdle.
It is.
So let's start with that philosophical bedrock. The one shared assumption, really, among almost everyone in the field is materialism.
Right. The idea that intelligence doesn't depend on anything, supernatural. No soul, no vital spark, just matter suitably arranged. That's enough.
But that immediately creates a huge puzzle.
A massive one. If we are just, as they say, atoms in the void, how do you get from physics to something that understands or fears or makes a plan?
And the crucial maneuver here, the materialist's answer is perspective.
Perspective. It's the argument that what something is depends entirely on the level you're describing it at.
So give me an example.
Okay. Think of a silk scarf. Under a high-resolution microscope, what is it? It's just a loose mess of frayed protein strands.
Right. Not very glamorous.
Not at all. But step back, put it in a display case, and it's obviously a shimmering, expensive accessory. Nothing about the matter changed.
Only the description we applied to it.
Exactly. Or a clockwork mechanism. To an antiquarian, it's a priceless piece of design. To a junk dealer,
It's just scrap brass.
it's scrap brass. It's the design and the function that transform the matter.
So intelligence isn't in the atoms themselves. It's a property that emerges from a very specific, highly organized description of those atoms.
Precisely. Which means the core question for mind design becomes, what are the constraints? What allows you to rightly regard something as intelligent? Is it what it's made of, its shape?
Or is it just what it does, its behavior?
And that focus on behavior leads us straight to the most famous thought experiment in this whole field.
The Turing test.
Alan Turing, 1950. He made this radical proposal that intelligence is really just a matter of behavioral capacity.
The test itself is so simple.
Deceptively simple. If a machine can have a conversation with you over a terminal, and you can't tell it apart from a real person,
Then we should just call it intelligent.
we should.
But why single out verbal behavior? That seems like such a huge simplification. It ignores walking, seeing, manipulating things.
It does. But Turing had this brilliant insight about language.
Which was?
He argued that talking, at one remove, it gathers up all other intelligent abilities inside itself.
Okay, unpack that a bit.
You don't need a robot that can play tennis. If you just talk to it about the physics of a spin serve or the history of Wimbledon, and it genuinely lacks those underlying abilities,
It would become painfully obvious very quickly.
very quickly, you'd expose the gaps, so language is a proxy for everything else.
That's elegant. It's a way of testing conceptual range without needing a $10 million robot body.
It is elegant, but it has a huge drawback, one we're still wrestling with, by focusing only on this abstract, disembodied conversation.
You ignore the real world, perception, action.
Yes, and it pushed designers for decades to overfocus on internal models and representations, forgetting that intelligence has to live in a body and cope with the messy physical world.
And speaking of internal states, that brings us to the classic mark of the mental.
Intentionality.
Right. The idea from Brentano that all mental acts, believing, hoping, fearing, are always of or about something else.
And for a materialist, intentionality is a massive headache
Why?
because of the paradox it presents. Intentional acts can be about things that don't exist. You can hope for a party that's never going to happen. You can believe in Santa Claus.
Ah. And Brentano used that, the mind's power to focus on non-existent things, to argue that the mind can't be just matter.
Exactly. But then you get the materialist counterpunch from Dennett. He proposes the intentional stance.
So what's the stance?
He accepts that intentionality is the mark of the mental, but he finds it in a pattern, specifically a consistent pattern of rational behavior in a context.
So it's not some magic stuff inside you.
No, it's an interpretive strategy. We predict a complex system's behavior by attributing beliefs and desires to it. We assume it's rational.
So if I see a chess program move its queen, I say it believes this is a strong move and it desires to win.
Yes. And you do that because it helps you predict its next very rational move. It's a holistic view.
And that solves Brentano's paradox, a false belief.
It's just an isolated lapse, a little flaw in an otherwise overwhelmingly consistent rational pattern. You only notice the blunder because the rest of the play is so good.
That's a powerful idea. But now we hit the big AI dilemma, original intentionality.
Right. We understand derivative intentionality. A sentence in a book is about photosynthesis because we, the authors and readers, mean it to be.
It borrows its meaning from us.
But an AI is an artifact. We built it. So is its intentionality just derived from us, its users. For mind design to truly succeed, an AI has to achieve original intentionality.
A mind of its own.
A mind of its own. And going by Dennett's stance, that requires active, rational engagement with the world, pursuing goals, making plans, and this is crucial caring, whether its beliefs are right or wrong.
Caring, that feels important.
It's everything. Which brings us right to the mechanism. How do you build a physical machine that produces that kind of rational pattern?
And the answer is computing. It all comes down to formal systems.
Right. A formal system is basically a game, like chess or logic, where you manipulate physical tokens according to a set of definite rules.
And the sources highlight three essential features here.
First, they are token manipulation systems. They are totally self-contained. The rules only care about the current arrangement of tokens.
The temperature of the room doesn't matter in chess.
It doesn't. Or the color of the pieces, only the position. Second, and this is the key to all modern tech, they're digital systems.
Okay, what does that mean in this context?
It means they are positive and reliable. Perfection is achievable because tiny physical differences don't matter.
Unlike an analog system like a sundial where every little imperfection throws it off.
Exactly. In a digital system, a voltage can be 4.9 or 5.1, but the system reads it unequivocally as a 1. It's insulated from that physical noise. That's what makes computation possible.
And the third feature?
They are medium independent. The identity of the system is in the rules, not the material. You can play chess with wood, plastic, or patterns of light. The form is all that matters.
And a computer is just one of these systems that runs by itself.
An automatic formal system, a physical device that manipulates its own tokens according to its rules.
Which leads to the core idea of programming, implementation.
And universality. Programming is just using one general-purpose computer to implement another specialized computer out of pure software.
And Turing's big insight in 1937 was that a universal machine can implement any well-defined formal system.
Any of them. Which means your phone, in theory, could run the rules for any thinking process if you just give it enough time and memory.
So the problem becomes about procedure. How do you structure the manipulations?
And you have two basic kinds, algorithms and heuristics.
An algorithm is a guaranteed method.
Guaranteed to work, always, in a finite time, like the steps for long division. A heuristic is a rule of thumb. It's reliable most of the time.
And you use it when an algorithm is just too big, too impractical.
Like finding the absolute best move in chess. It's theoretically possible, but it would take an Earth-sized computer eons. So we use heuristics to estimate the best move.
And here's where that idea of perspective comes back in.
And he does. A chess computer flawlessly executes its algorithm for calculating position strength. At that level, it's perfect.
The low-level calculation, the syntax.
Right, but that calculation is itself just a heuristic and estimate about its chances of winning. That's the semantics.
So when the computer makes a blunder, it didn't fail its algorithm.
No. It succeeded at the algorithm, but the heuristic itself was flawed in that specific context. It's a mistake of perspective.
This whole idea that rational thought could be mechanized through formal token manipulation, that launched the first great school of thought.
GOFAI.
Good old-fashioned AI.
The idea that the mind is a digital computer. That thinking is just the rational manipulation of internal symbol structures.
So the tokens aren't just tokens anymore, they're symbols, they mean something.
They have to. And this requires semantic interpretation. You have to find a pattern that makes sense, like decoding an ancient language. The best translation is the one that gives you the most detailed, sensible story.
But GOFAI hit a massive wall almost right away.
Oh, yeah. The common sense problem. These early systems could be brilliant at one narrow thing, like proving theorems.
And deeply, deeply stupid about everything else.
So stupid. If they hit a situation that wasn't explicitly programmed, they'd make blunders a 3-year-old wouldn't make.
Which meant later GOFAI became obsessed with knowledge representation.
Just trying to catalog all of common sense?
Yeah.
An impossible task. And, maybe most importantly, GOFAI was terrible at general pattern recognition. Faces, voices, things like that.
Which spurred a revolution.
A complete conceptual shift to NFAI, New-Fangled AI.
And the most famous version is Connectionism.
Right. This rejects the whole central processor idea.
Yeah.
Instead, you have networks of simple units with weighted connections, all processing in parallel.
They're essentially pattern processors.
That's what they do. They excel at finding similarities, recognizing incomplete patterns, associating one thing with another, exactly what GOFAI was bad at. They're inspired by the brain.
And there's a key technical distinction here that gets missed a lot. GOFAI is a digital formal system.
Yes.
But connectionist systems are often fundamentally analog. We just use digital computers to simulate them.
Like a weather simulation. That's a crucial architectural difference. And it creates this huge clash. GOFAI is great at syntax, logic, sentences. Connectionism is great at raw pattern recognition. And since language is so central to intelligence, that's a big problem for NFAI.
But that wasn't the only reaction. There was an even more radical movement.
Embodied and embedded AI. They took the drawbacks of the Turing test to heart.
And their argument is that intelligence isn't all in the head.
Not at all. The intelligence system is the larger whole. The system, its active body, and the environment it's in.
And this came from the practical difficulty of robotics.
It was crushing. Trying to get a robot to unlock a door by having it build a perfect internal mathematical model of the lock, the key, the hand, it's just computationally impossible.
So instead of that, they proposed the insectile approach.
Avoid central computation. Use crude local detectors. Use the physical flexibility of the arm. And use the environment.
Like what?
Like building a big funnel around the keyhole. The funnel physically guides the key in. The environment does the heavy lifting, not some massive internal brain.
So this totally changes what we even mean by knowledge.
It does. It means so much of our human expertise is embedded outside the head. It's in our bodily skills, our reflexes, the very shape of a hammer.
We're intelligent because we live in an intelligently structured world.
Exactly. So you have these two powerful competing designs, GOFAI with internal symbolic reasoning and NFAI with parallel processing and embodiment. Both are trying to create a system that can take the intentional stance.
To show consistent, rational behavior.
Yep. But even with all this progress, there's a final nagging complaint leveled at both camps. That neither of them pays any real attention to feelings, consciousness, or understanding.
Right. The sources draw a really sharp line here between knowledge and genuine understanding. This is the ultimate barrier.
The philosopher Haugeland lays out these 3 incredibly demanding conditions for a system to achieve true understanding, to turn its internal labels into proper concepts.
Okay, what's the first one?
The system has to take responsibility for applying its concepts correctly. It has to know when an application might be questionable.
And the second is even harder.
Much harder. It has to take responsibility for the adequacy of the concepts themselves. If its concept of chair keeps failing, it has to be able to revise what chair even means.
And the third?
It has to take a firm stand on what can and cannot happen in the world. It has to be able to recognize when something happens that contradicts everything it believes, and then try to figure out what went wrong.
So the crucial distinction isn't just producing outputs that we think are true.
No. It has to appreciate the difference between truth and falsity for itself. It has to realize that it must yield to the world, and it has to care which is which.
It has to care.
That's the missing piece. That internal valuation of truth is what defines genuine intelligence.
Which leaves the whole field in this fascinating state of tension. You still have the GOFAI camp betting on symbol manipulation and the NFAI camp betting on pattern recognition and embodiment.
Both trying to build a machine that acts rationally, but arguing over the fundamental architecture.
Which brings us back to the ultimate question.
It does, and it's one for you to think about. If an AI system gets so good, it can pass any Turing test you throw at it. If it acts perfectly, rationally, consistently, are we justified in believing it truly understands its own beliefs and desires?
Or is it still just an incredibly sophisticated machine going through the motions?
Exactly. Is there a person in there who actually cares about the truth?
Yeah.
That gap between behavior and understanding, that's still the ultimate challenge for mind design.